Hello everybody, welcome to this lecture on solid state physics. Today we'll be talking about different types of solids, polycrystalline, crystalline and amorphous type of solids, and we'll also be looking at crystal lattice and how do we define crystal lattices mathematically. So to begin with, we understand that in the gas phase, the atoms and these molecules, they do not bond to each other. So essentially, whatever enclosure that they are in, they are free to move around. Okay? So there is no idea of ordering that exists in the gaseous phase. So similarly, in liquids, these materials they don't have any atomic or molecular order. Okay, so they can assume any shape of the container that you put them in. Okay, however, there are materials like liquid crystals, which are now present everywhere. You have liquid crystal displays in your phones, in your computers, and essentially these are basically molecules that have some permanent dipole. And as soon as you apply some external electric field, these dipoles they align themselves towards the electric field, and so you have some short range order that develops. Okay, so we will not be talking about liquid crystals per se, but I just wanted to put it out there that you can have some intermediate cases as well. But for most of the scenario that we are dealing with, the liquids essentially they don't have any atomic or molecular ordering, and the bond that exists between the liquids is very weak, and so it can be easily broken if you apply some thermal energy or heat. You can easily evaporate the liquid. So unlike these two phases, solids are very different. So in solids you have atoms or molecules that vibrate essentially about an equilibrium position in space, and we understand that that vibration happens due to some thermal motion that might be present because of some thermal energy in the system. And these solids can be of different types. You can have crystalline solids, you can have polycrystalline solids, or you can have amorphous type of solids. So here you can see some examples of an amorphous solid here, and you can see that it looks very different from a crystalline solid. Okay? So these solids essentially they have very strong bonds between them, and much stronger than the liquids. Okay? And because of the strong bonding, you definitely require more energy to break these bonds. Okay? So let's look at this classification a little bit further. And essentially, this classification into crystal, polycrystalline, and amorphous types is basically deal with the size of the ordered region that exists within the material. Okay, so when we are talking about an ordered region, essentially what we are saying is that there is some spatial volume in the solid in which the atoms or molecules they have some regular arrangement, and because it's repeating arrangement, so you have this periodicity present in your solid. Okay, so depending on the size of this ordered region, you can classify solids into these three types. So essentially, if you look at the first type, the crystalline solid, these are basically substances in which the atoms or molecules are arranged in a well defined repeating pattern, three-dimensional. Okay. So here, for example, you have a pattern of an atom depicted in red and a blue one, and then this repeating unit basically repeats itself throughout the crystal. And if you take and consider that this high degree of order, right, is present throughout the entire volume of the material, then you are dealing with something that is called single crystalline materials. Okay, so single crystalline materials they have a very high degree of order that can be present in the entire volume of the material. Okay, and essentially what we are saying is that the single crystal has a property of basically translational symmetry, in which essentially suppose you are moving from a solid in the second position to the fourth position, then the environment space that this essentially the atom sees is exactly the same as the space that the atom sees here. Okay, so there is essentially no difference between these atoms. Okay, so these single crystalline solids are very important because later in the course you will realize that the electronic properties of the materials, they depend heavily on the crystal structure. Okay, and when it comes to semiconductors and other materials, the electronic properties are the key as to how they actually function. Okay, so very important materials. And then you have the other classification, which is polycrystalline solids. And basically, in polycrystalline materials, we have aggregates of many small single crystals. Okay, so basically, you have these single crystals which are very highly ordered, and but the length scale of this single crystal is not throughout the entire volume. Okay, essentially, you have these grains that are present, and inside a grain you have basically this long range order, and all the atoms are arranged in a particular fashion, and as soon as you go to the next grain, you can see that the order and the pattern completely changes. Okay? And so they are divided by this well defined grain boundaries. Okay, and basically these grains that you get, they usually range from anywhere from 100 nanometer to 100 microns in diameter. Okay. So in most of the cases, you always encounter materials that are polycrystalline. Okay. And in polycrystalline materials, if you have grain sizes that are less than 10 nanometer in diameter, so then basically you are reaching this nano regime. So they are generally called nanocrystalline materials. Okay. So similarly, the third type is amorphous solid, and as you might have predicted, these are basically randomly oriented atoms. So they do not have any well-defined patterns or structures that are present, and the ordering is probably only about a few atomic sizes. Okay, and there is no presence of any long-range order, and so the way these materials behave, their properties are very different from your polycrystalline or crystalline materials. Okay, and some of the examples are some of silicon and glasses, which are basically amorphous. Okay, so well, to think about it, is there any perfect crystal out there? So strictly speaking, you cannot really have a perfect crystal. Okay, because even if you think about it, the surface of a crystal where the entire volume ends, so it's actually an imperfection, right? So basically, you're having arrangement, and at the surface, you're basically breaking this arrangement, right? And moreover, you might have a scenario where most of the crystals, if you look in nature, they have some impurities are there, and of course there are some thermal vibrations that might happen that might create movement of these atoms. So there are cases in which you don't actually find the perfect crystal in nature. So I just want you to keep that in mind. So essentially, when we are trying to read about these crystals, basically we are involving ourselves with the science of crystallography. Okay, and crystallography basically deals with the geometric description of the crystals and how they are arranged. Okay, so for a solid state physics course, it is very important to know about the different crystal systems and different symmetries of the crystals, because depending on how you classify the materials, you will see that they have a very profound influence on its properties. Okay, so we have to look at some crystal structures, and we have to distinguish between them, and they should be unambiguous in their description, and so that we can clearly understand what is happening with them. Okay, so later you will see that the structures, they will be classified depending on what symmetry they possess. Okay? So a basic knowledge of this crystallography is very important, and that is what we will be trying to achieve in the first unit of this course. And so to understand different types of crystal structures, the first thing we have to understand is something called what is crystal lattice, okay, or a space lattice. So when we are dealing with crystallography, we are concerned with the geometrical properties of the crystal. Okay, so basically what we do is we take every atom and we just replace the atom by just a geometric point that is located somewhere inside the crystal, and that signifies the position of an atom. Okay, because as you might be aware of, the atom basically has a nucleus and electrons and all the stuff. So, but we are reducing down to just a point. Okay, and then we are looking at this geometric arrangement of these points, which is your crystal lattice. So, basically, we are defining a crystal in saying that this crystal will be formed when these atoms, they will arrange themselves in a periodic fashion. Okay, so that they build these identical blocks that you can just replicate and create the entire structure from. Okay? So, for example, here you have a block AOPC, and so if you keep replicating this block, then you will end up with the entire structure of the material. Okay? So because there is order present in the materials, so you will have some anisotropic properties and some discontinuous properties. So you won't have a homogeneous property because there is ordered, so there is preferred orientation of these properties. Okay? But essentially what we are saying is that these atoms are arranged in this infinite array of points in space, and each point has basically identical surrounding to the others. That is, if you have a point A, whatever environment it sees around it is the same as this point D, and it will see the same environment around it. Okay? So once we start looking at this problem mathematically, basically what we are doing is that we are looking at two things. We have a space lattice that is just these points that are located in space, and then there is something called a basis. Okay? And this basis, the identical group of atoms that is present in a structure. Okay? And essentially what we are doing here is, suppose you have a basis with two different atoms. Okay? And this is your repeating unit. So you will take the basis and you will keep the basis at each of these space lattice points. And if I keep repeating this pattern on the space lattice, and once you do that, eventually you will end up getting the entire crystal structure of your material. Okay? So you have to be careful so that you don't mix up your atoms with the lattice points. The lattice points are infinitesimally small points in space, and they do not have to necessarily lie in the center.